So, welcome back, and today we are going to talk the chapter on ray optics, and we will also discuss optical instruments. The ray optics, we deal in visible radiations which have a wavelength from 400 to 750 nanometers, and this is the spectrum we give. Okay, starting from here, from here we give, and the speed is said to be about 3 into 10 to the power of 8 meters per second in vacuum. That is something called nothing. Okay, in free space. This speed is enormous, quite big. Okay, and this is one thing, that the speed is enormous, and the other thing that we ought to know is that they travel in straight line. Okay, although in the last discussion on electromagnetic waves, we did learn that all radiations from long radio waves up to gamma rays, they are basically waves, but we'll take the light to be traveling in a straight line because the normal objects which we deal in the ray optics, they are the size of centimeters or more, and the wavelength you can see that is in several tens or hundreds of nanometers. It's very, very small. So now we define ray of light traveling between 2 points, a straight path which has been shown here by the green line, and the beam of light which can be parallel set. There are so many rays between this and this, so many rays between this and this is diverging, and this is converging, and this is traveling in a straight path. Okay. Well, reflection of light by spherical mirrors. So first of all, I'll tell you about the principle of reflection. If there is an incident ray and it is coming on a surface which I have just shown you to be a plane surface, then the incident ray, the reflected ray, and the normal at the point, whether it is a plane surface or whether it is making a concave or convex surface, it's always that all these three lines, one thing is that angle I is equal to angle R, and the other thing is that this and this, they are in one plane. They are co-planar on the same plane. Okay. Now let me define paraxial rays. But before that, I will define for you the pole, the center of the spherical surface. This is an important thing. Or the optical center in the case of the spheres. Okay, that is also the center of that instrument, the lens. And then we define an axis as the principal axis. Suppose this is a spherical surface, this is the pole, and the line joining the center of curvature and the pole of the spherical mirror, that is called the principal axis. Let's define more things, and that is, let us define paraxial rays. Paraxial rays are those with the incident at points. Oh, where is my friend T? Okay, at points close to P, okay, and make small angles with the principal axis. So make points close to P and make small angles with the principal axis. Okay. Now, for the spherical mirrors, as also for the lenses, we follow a convention, and the convention that we are going to follow is Cartesian sign convention. Cartesian is from Descartes, who gave us the three axes x, y and z axes. Okay, so we take this as the x axis. There can be objects on the left, and we understand that here that it is the rays are traveling, incident light is from left to right, and here I have just shown the spherical mirror, which is a concave mirror. So it's very simple, the convention is very easy. Following Cartesian coordinate system, what we have, that the direction of the incident light is taken as positive. Okay, the distances against the incident light, they are taken as negative, and the distances along the incident light are taken as positive. So these are negative and positive. Okay. How about the distances along the perpendicular axis? So above this x-axis, if it is up the axis, then horizontal axis, then this is called positive, and these distances are taken as negative. Okay. As a result thereof, we find a single formula that results for the mirrors, and in the case of lenses also a single formula exists for the same convention, set of convention. So life is easy for us. Now let us define what is the focus, principal focus, and the focal plane. Okay. Now parallel rays which are parallel to the principal axis and they are coming here, they pass through a point or converge at a point, okay, which we call the focus. It is an actual point at which the rays are converging. But in case this is like this, then they diverge, the rays diverge. We will show with the proper diagram, and they appear to be coming from, okay, starting from a point on this right hand side. So the focal length becomes positive in that case and negative in the concave case. Okay, so then we take the various cases one by one. So friends, we are going to draw the diagrams. Just try to be as close to reality as possible. So what happens is, I have taken parallel rays in the case of concave mirror, which has got the center of curvature C and something which is defined as focus over here, and this is the pole P. So look here, what happens basically is that this ray is coming and this will go out through the focus. Okay. If I draw a line from here to the center of curvature, then that line will bifurcate this one. Okay. So any line like that. The ray which is coming along the principal axis, CP, that ray after deflection it goes back up in the same direction. Incident rays are shown by a single arrow, and the reflected rays are shown by double arrows. Okay. So what happens is that for all this set of rays that we have, one of them, all of them, they pass through this point over here. Okay. So, which we call the focus. In the case of concave mirror. In the case of the convex mirror, you can see that a similar thing happens. All parallel rays to the principal axis. This one, because it is heading towards the center of curvature, so it goes back in the same direction. And this one, after that, it is reflected back. And if we connect C with this, then it will be furcated in two parts. Angle I is equal to angle R, like that. Similarly from here, 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 everywhere. So we find that the reflected rays, they appear to be coming from a point F, and they diverge after being reflected from the convex mirror. Okay. Now, let us take a very simple diagram that we have for the concave and for the convex mirrors. Look here, this ray is coming here and it goes through the focus. Okay. If I connect the point C with M, then these two angles are equal. These angles we take as theta and theta respectively. Okay, so this total angle makes 2 theta. And the alternate angle over here, this also becomes equal to 2 theta. This angle becomes equal to theta. As you can see that this is also an alternate angle with this angle. And similar kind of geometry is present in this case also. Okay. When the ray is coming parallel ray, of course the parallel ray which is coming like this will be reflected back because it is heading towards the center. But I have just shown that this ray is diverged in this direction and it appears to be coming from this point F. Okay. And if I connect the point C to this point, then it furcates this total angle. So this angle becomes equal to theta, and this angle also becomes equal to theta, and this angle being an alternate angle, this is also equal to theta. Okay. So these are the set of two diagrams that I have made for concave and convex mirrors. Okay. Now, for example, let us take this, and the focal length F is equal to Fp from here to the pole. Okay. What we do in both cases, that from the point of incidence M, we drop a perpendicular MD here and also over here. Okay. So, and the radius of curvature, that is from C to P, that is taken as R. No problem. Now look here. Angle MCP. Angle MCP. Okay. The angle MCP. Okay. This is theta. And angle MFP. Look here. MFP. Okay. This angle is equal to theta. Okay. So tan of theta, because we have MD, and from the trigonometry I can show that the tangent of theta is equal to MD upon CP. Okay. And tangent of 2 theta is equal to MD upon FP. Okay. Now, because theta is, if we take theta to be small, then for small angles, tan theta is approximately equal to theta. So tan 2 theta is also, 2 theta is also small, so this will become equal to approximately 2 theta. And therefore I can write this value, okay, MD upon FP or FD, sorry, MD upon FD is equal to 2 times MD upon CD. So FD will become equal to CD upon 2. So this is what we get. Okay. This is the relation that we get. We can confirm from there. Now again, for small theta, D is very, very close to P. Okay. So that for this relation I can write FP is equal to CP upon 2. Okay. Because D is approximately at this point P. Okay. D is approximately at this point P, the pole of the mirror. And then naturally what we can write is that FP is the focal length and CP is the R value. So F is equal to R by 2. Okay. So I will cut this preliminary lecture at this stage. Okay. So in both the cases, the focal length is equal to radius of curvature divided by 2. So it shows that if the mirror is less curving, then the focal length is more. Less curving means R is more. Okay, because I told you that there is a relation between curvature and radius of curvature. Radius of curvature is equal to 1 upon curvature, curvature is equal to 1 upon radius curvature, and that is a relation of inverse kind of proportionality exists between the two of them. So more the curvature, that is less this value, less the value of F. Okay. So this is about the mirrors, and next we apply this thing and draw ray diagrams to understand and to obtain the formula which relates the object distance and the image distance and the focal length with each other, also the size of the object and size of the image, whether it is actual image or whether it is virtual image. So we'll talk about that in details, and you just, I advise that please go through that, scribble it yourself, make the approximations work, and be happy to find that the focal length is equal to the radius of curvature divided by 2. So it is just in the center of the line joining the curvature and the center of curvature and the pole, and just in between them. One more thing I would like to tell you, and that is, if I have paraxial rays, okay, and they have an inclination to the CP, that is the principal axis, then of course they will make a image in the focal plane over here, just like this. Okay, so you can draw that diagram also. I have left it for you. Okay, so anyway, it is a long time that I have done the geometry and enjoy doing that geometry, and you know the geometry and you can do it and enjoy it, but do scribble at least 2 times to obtain this result, and must be as close the curvatures that you draw. Sometimes the students will draw like this and the C value will be here, at that point they will put the F value. So try to use the compass and draw the diagrams as close to reality as possible. Thank you very much.